Okay, so in this video, um, I was recently working on an incline plane problem, just very basic beginner one, and um, there was something so there was a way that I wanted to do it that I thought would work, that didn't work, and I eventually was able to find out why it didn't work, and so that's kind of why I'm making this video, is to show why it doesn't work. Um, So I have some information written here already. The information that we're given is there's a box that's sliding uphill. It's being pushed, or somehow it's got some force pushing it up an inclined plane. The mass of the box is 50 kilograms. The angle theta that the inclined plane makes with the horizon is 16.3 degrees. The force that's pushing it up the hill is 250 newtons. The uh, coefficient of kinetic friction is 0.2. That's what we're given, and we're supposed to find the acceleration with which it's moving up the inclined plane. And yeah, I didn't label everything there, but I think it's pretty clear what forces are acting on it. So we have the force, I'll just call it pushing force, pushing it up the hill, the force of gravity acting perpendicular to the horizon, the normal force acting perpendicular to the inclined plane, the force of friction preventing slowing the motion uphill. And if you were to sketch this out, on one of these doodads, and I cannot remember the name, what do they call these things, a something something diagram, I think. But anyway, so if this represents our 50 kilogram box, then this would be the pushing force that makes angle theta with the x-axis and the y-axis. And this is the normal force kind of legible. This is a right angle because the normal force pushes at a right angle to the surface. If this is a right angle and this is shifted up by theta, then this is also shifted this direction by theta. The force of gravity acts straight down. Force of gravity. And the friction force, is parallel to the pushing force, kinetic friction, given in the problem, which makes this also theta. So now if you look up anywhere, or maybe you just already know how to do these, or everybody says to make the direction of acceleration line up with one of the axes, because you can rotate these axes however you want. The x and the y axis, I drew them the way they're standardly drawn, up and down, and it's not but it's not necessary to do it that way. And in fact, for these type of problems, you don't want to do it that way. You want to shift this x around so that the pushing force, which the acceleration is moving in the direction of the pushing force, it's given in the problem. So you want the x-axis or the y-axis. In this case, though, it makes more sense to line up the x-axis with that force so that it's lined up with the final acceleration. But once again, the reason for this video is because I wanted to know why. And so found out why. I'm going to demonstrate after first solving it the easy way. Well, let's make that a little better. Okay, so these are axes again. Once again, this is still x, y. But let's shift these so that this is the pushing force. This is the Force of friction. These are obviously not to scale. The force of friction has to be smaller since we're moving. I think that's a little bit smaller actually, so maybe we're moving slowly. This is the normal force. And now, since these all got shifted clockwise by theta, Fg, which was along the y-axis, is going to be shifted by theta also clockwise. So it's theta in, supposed to be theta, this direction. So now the problem looks a lot nicer as far as trigonometry is concerned because there's only one force that is not aligned with the axes. I'm drawing over here. So to solve this, we need to use, I think it's Newton's second law. Sum of the forces equals mass times acceleration, which equals, in this case, we don't have to worry about the y direction. We just know from the setup of the problem and from physics in reality that this box is not sinking into the inclined plane and it is not flying off of the inclined plane in an upward direction. So the net force in the y direction is 0. So we will have no acceleration in the y direction. We only have acceleration in the x direction that is according to this axis right here. I mean, not axis, according to this plane. In this plane, we would have acceleration at an angle. So we would have y and x acceleration. But in this plane, we only have acceleration in the x direction. So we're only concerned with the sum of the forces in the x direction. We have a positive pushing force. I guess I don't need to write the, I don't know if I should call it the x component of the force or not. It doesn't matter. The magnitude is the same. So the force minus pushing force minus the friction force, which is kinetic friction. I want to draw like K every time, but kinetic friction, minus, there's a little bit of force of gravity pushing in this direction. That would be this little piece right here is pushing in the negative x direction. So force of gravity, now this is the x component. Not the whole force of gravity, it's just the x component of the force of gravity. Now, we can find some of these things. Let me get another color, red. So force we were given, the pushing force, the magnitude of the pushing force was given. We were not given kinetic friction, but that equals mu kinetic, which we were given, times the normal force. We were not given the normal force. The normal force, in this case, will equal the y component of the force of gravity. So we need force of gravity, the y component of the force of gravity, which, that's this right here. This is a right angle. There's theta. This is the value that we were given. I'll just write f of g again, but f of g, make sure to erase that. F of g is mass times g, mg. So over here, f of g is at an angle, but in our original problem, f of g is not at an angle. It is completely downward, and this magnitude is the same as this magnitude here. So this fg length of the hypotenuse here is going to be m times g. Technically it would be negative, but I'm not going to worry about signs in any of this part right here because the signs that I want were already decided up here. So I don't need to worry about them down here because when I plug everything in, I already will have the signs I want because of the way I set up the problem, the sum. So if this is mg, this value right here is adjacent to the angle, so it becomes mg cosine of theta this value is opposite, this component is opposite the angle, so it becomes mg sine of theta. And so in the y direction, we have mg cosine of theta. Then that means that the friction force equals mu times mg cosine of theta. This one would be positive because it's opposite in direction. If I were paying attention to signs at this point, which I'm not. Then we need the force of gravity in the x direction, which equals, once again, this would be negative, but I don't need to worry about it because I already set it up as negative in the problem above. So this is mg sine of theta. And let me just double check so I don't have to. Where did I write that at? Yeah. Okay. So now, rewriting this sum down here, we have mass acceleration equals the force that we were given minus kinetic friction force, which is mu times mg cosine of theta minus force of gravity in the x direction, which is mg sine of theta. And the one mathy thing that's nice to do to this before plugging everything in, you could plug it in now, but you can divide both sides by m. On the left-hand side, these m's cancel. On the right-hand side, m does not cancel with anything in the first term, so that's still going to be divided by m, but these other two terms each have something that cancels. So we're left with, our final formula is acceleration equals the pushing force divided by the mass minus mu times g cosine of theta minus g sine of theta. I could pull out the negative g from both of these, but there's really no point to it. It doesn't actually make it any faster to type. And when we plug all this in, I'm going to use Desmos. I absolutely love their calculator. Over to where I can see it. So we have the force, which was 250, divided by the mass, which is 50, minus mu is 0.2, times g is 9.8, cosine of theta was 16.3, minus 9.8 times sine of 16.3, and that looks correct. Let me just double check. Yep, 386. So, if I can find my mouse here. So we have acceleration equals point, there we go, 0.368 meters per second squared. I didn't follow my units through, bad physics student. So this is the answer. That was the easy way. Now, I want to do it the hard way, which, I mean, it's harder as far as the math is harder, but it would have been easier had it worked. So far as trying to remember something new, some new problem solving thing to remember for an inclined plane problem when there's so many other kinds of problems to keep in mind. I prefer to remember the math, but anyway. So going back to, pick a new color. See how well blue shows up. Yeah, it's not bad. All right, so let's go back to this setup right here. This is what I kept trying to do, was use this setup, and I couldn't figure out why I was getting the wrong answer, and I'm going to demonstrate why. I don't have this planned out exactly how I'm going to explain this, so it's probably not going to be real in a real nice orderly fashion, but okay, so if I redraw this for absolutely no reason, I just started to redraw it. So we have, once again, this is the y-axis, this is the x-axis. The force of friction goes at a 16.3 degree angle that way. Force of kinetic friction goes that way. This is theta, theta, perpendicular, normal force, so this is theta. And our one force that lines up with the axis, if you draw it right, is the force of gravity. So in this case, our acceleration, oh yeah, I was going to use blue. All right, so in this case, our acceleration vector goes in this direction, parallel to the inclined plane, parallel to the force and kinetic friction vectors. Push force. I should say push force because force, they're all forces. It doesn't make any sense. Okay, so we have this. So that means we would have to solve for acceleration component-wise, and then how do they say it? I think they say adding in quadrature. So we would have to take the sum, square the x component, square the y component, and add them, and then take the square root of that. A squared plus b squared equals c squared. So our goal would be to find the acceleration in the x direction, square it, plus the acceleration in the y direction, square it, take the square root of this, and this is going to equal the acceleration vector. So if I draw another set of axes, because I'm obsessed with drawing axes, and imagine that this time I'll use gray for everything. So these are the forces: pushing force, normal force, friction force, and force of gravity. Now, our acceleration vector is going to run like this at some length. I don't know what it is yet. Well, I mean, technically I do. It's right here. This is the length. But, had I not done it the easy way first, I wouldn't know the length. So it will have a y component and an x component. And so this is a, or like, I don't know if it's better to say the magnitude of a or just a. I mean, it's both because this is also the direction, but really what I'm concerned with there is actually just the magnitude. This is ax, and this is a y. So if we add these, you square this, add it to this one squared, and then take the square root, that equals this. A squared plus b squared equals c squared. And once again, this is theta. It's kind of clear to see that from the setup here, which was given originally in the problem. So you wouldn't have to do this way. You could also, you could say, so if this is the one that you want, you'd say like sine of theta equals opposite, which is ay, over dA. I'm going to keep the vector symbol there. So yeah, whatever. A is a vector. I don't know how to say that better. Then we would be solving in this case for A as a vector, because if we do it this long way, that'll be what we don't know. So we would say A vector equals AY divided by sine of theta. Do the same thing, and you could also say that acceleration equals AX over cosine of theta. Or if you don't like trig, you could say trig functions, you could say it equals the square root of AX squared plus AY squared. Yeah, like that. So let's erase some of that. Too much space. Lava. Man, that takes forever. Green. All right. Okay, now, but back to the problem. So what I wanted to do was the same thing that I did down here. We went from the force of gravity and we drew a line perpendicular to the y-axis, and we said that the hypotenuse was f of g. And I don't, if I don't end up saying something stupid on the video, but let me use a different color. I don't want to sit there and erase it, but I also don't want it to look like it's meant to stay. So basically like this. And let's not do that one. I'm not really that worried about that force. Let's just do that one. It worked for, I'm trying to remember if it worked for any of them. I didn't sit there and test out. No, it was this one right here that I know for sure it does not work on. So if we try to do it the way that I just said, and we make this a right angle, this does not yield the right answer. And the problem becomes that this force of gravity, I do not know that the force of gravity would be the correct length right here. So they would make a right angle with this length of the normal force. The reason you can do it over here is because the only thing that you are, gotta say this, the only one of these three sides, the hypotenuse or either of the two sides here, the x component or the y component, the only one that is, I want to say actually exists, or these two, the x and the y, are arbitrary. They're not dependent on anything else in this graph. So I can make whatever I make this x, it doesn't have any dependency on the friction force, the normal force, or this force. And the same is true for the y component. The only one that has any relation, I guess, the only one that has any dependency on the given information is the hypotenuse here. And these two are only dependent on the hypotenuse and each other. So I can make this a right angle, no problem. I just draw this over, and wherever it happens to be to make a right angle, that's what I call it, and it's good, and it works out because this becomes parallel to the direction that, parallel to the line that the acceleration will be on, and so it works out. Over here though, this length, we'll just call this force normal y, which that's what it is, and this is force normal x. So in this picture, my pink picture here, force normal y is actually dependent on the force of gravity. So I can't just arbitrarily make this whatever length I feel like it. It needs to be a certain length based on the other items in this setup. But this normal force also needs to be a certain length based on the items in the setup. So these two lines right here are not arbitrary. And if two of the three lines in a triangle are not arbitrary, then neither is the third line. Every one of these lines has to be a certain length. And so if I were to take this and let's just take one of the things, for example. So this is the normal force, and in this problem, the normal force, actually the way I have it set up, the normal force pushes in the negative direction, the force of friction pushes in the negative direction, and the force of gravity can be ignored. So I would look for the x component of the normal force to, this is incorrect, okay, but what I was wanting to do was look for the x component of the normal force in this direction, and take that as one of my forces that I'm summing together, and then use the normal force, which I think I was wanting to use this force right here. But you'd have to calculate that based off of, because this force equals this force, and you use that to calculate this force. So then you can use that to calculate the magnitude of the frictional force right here. And then once you calculate the magnitude of the frictional force, then you could calculate the x and y components. Which actually, yeah, but so the reason that doesn't work, as I was saying, because the only way for me to calculate this Fy of n, the only reasonable way, I'm trying to think if you could do it. Well, yeah, the leaving the picture like this, the only I don't know how to say it. If you want to think about the problem conceptually in this layout, then you would want to try to calculate the normal force y component based off of the force of gravity, like directly, but you can't because this length does not equal this length. What you do know from the information is that this hypotenuse length, the actual normal force, let's say the magnitude of the normal force vector, there we'll get a little magnitude sign in there. Oh, it's hard to do. That is equal to this component of the force of gravity, which it's over here what I call the y component of the force of gravity. Over here though, it doesn't line up with anything in my axes. I guess this would be like angle 90 minus theta. So it's the, anyway, you see where I'm going. So you could use the force of gravity to calculate this length, use that to calculate this hypotenuse, the magnitude of the normal force, then use the magnitude to calculate these two sides. But in essence, what you did is the exact same stuff we did here. So there's no benefit whatsoever to not rotating it, because in the end you do the same stuff, but it looks a lot messier. So I'm gonna have to draw this another time. So, because that looks like a mess. So let's draw this again. Get back to blue. Now, basically, to use the axes in this way, what you would end up, what you would end up doing in essence is, as I just showed, extending this line down, calculating the magnitude of the normal force based off of this, and then you would extend this line over like this so that this is a right angle. That looks like that's supposed to be gray. But now, really what you've done, sorry, got on multitask. Well, now what you've really done is you've done the exact same thing as rotating it. You just have an axis here, an axis here, and you really might as well have rotated it at that point. And the way that I figured this out was a little bit of a roundabout way, because I was having troubles finding this exact stuff that I showed you. But I figured that, oh, let's see, what was the first thing that I did? Oh yeah, okay, so I knew, which one was I working with? The acceleration. So I knew what the acceleration was based on the easy way. So let me just rewrite that right here. Oops. How about right? Oh, let me choose a different color. It's really starting to look like a mess. So acceleration, as we found the easy way, the magnitude of the acceleration vector is 0.368 meters per second squared. Now I know this information, and so if I can take this messy one right here, in this layout, I know that this length, this is This originally I drew as the force vector, but let's just pretend now this is no longer the force vector and this is the acceleration. If this line represents the acceleration, then this is the magnitude of the acceleration. This is the acceleration y component. This is the acceleration x component. So this squared plus this squared should equal this squared. So then I know this angle as 16.3 degrees, as that was given in the problem. So now I can use trig to say that AY equals the magnitude of the acceleration vector times sine theta AX equals magnitude of A times cosine of theta, which I think I already have those written down. Yeah, so the y component is 0.103355. It's meters per second squared, but I'm going to ignore units because it makes me happier. So, and in the x direction, it is 0.353446. So I know that information. Now I can go back to, I really need to stop redrawing this image. I can go back to this and start to calculate all of those forces. Let me just check real quick. Is that really what I did last time though? Because somehow I got to the actual. Okay, yeah. So you could do that. I didn't actually go that far with it though. Last time I switched to. The other thing is I know that over here I calculated, or I could have calculated, the normal force equals mg cosine of theta. Excuse me. Equals mg cosine of theta. So if I were to plug mg cosine of theta into a calculator, I should get 470 newtons. We'll keep it 470 newtons. So I know that in this picture, that magnitude's the same. Even though you rotate it, the magnitude won't change. So this is 470 newtons. This length right here, I also already know because I know f of g, which f of g is just mg. So it's 50 times 9.8, and that is 490, yeah, 490 newtons. And that is actually what tipped me off to realize that in this setup, this is the hypotenuse. If I want to get the same values, that would like work out nicely. Yeah, so this is the hypotenuse, and you're basically going to end up with the same thing that you have over here. So anyway, that's kind of a little bit about why it's better to keep things to rotate the axes so that the acceleration lines up with one of the axes. I think that's an important part of what allows you to make these component vectors right angles with the axes, like is typically done. Because if you don't do that, when you start plugging in numbers, how to say that, this this value is not actually force normal y. Well, I don't want to say that. This could be force normal y, but when I draw my triangle this way here, force normal y does not equal FG, because if I were to, as you can see from here, from how this is rotated, FG, let's see, so yeah, no. Force normal, I don't want to say this. No, that's not true. Force normal y does equal FG, but it is not, it's like I can't say it right. So force normal y, if force normal y equals mg, then this is not a right angle, which was shown in the problem, because we know from the final solutions that this hypotenuse needs to be 470, because we found it the traditional way of doing the problem. It's supposed to say 470 newtons. If we take force normal y to be FG, let's just pretend that we're true. So we would have force normal y is equal to mg. Once again, I'm ignoring signs because it's gonna be easier just to plug in the signs at the end where it makes sense. So force normal y is equal to mg. So from this setup, we have cosine of force normal y equals, I'm just going to keep this actually, this is mg, but this is force normal y. Like, well, let's just say for the sake of argument that it were true. So force normal y equals mg. Force normal, so yeah, we would have cosine of theta equals adjacent, which is force normal y, over hypotenuse, which is force normal. And in this case, force normal would be the thing that we don't know, because assuming, for right now, for the sake of argument, we're assuming that force normal y equals mg. We were given theta, we were given m, we know g. So force normal is the only thing we don't know. So we're going to have, yes, we're going to have force normal equals force normal y over cosine of theta, which equals mg over cosine of theta, which equals 50 kilograms times 9.8 meters per second squared divided by cosine of 16.3. So 50, 9.8, 16.3. Honestly, I forgot already. 50 times 8 divided by cosine of 6.3. Oh, 16.3. This is telling me it's at 510. So this is equal to 510 newtons. But we know that that's not true. Force normal is supposed to equal 470 newtons. So it does not work.